Yeah, as just mentioned, today I'll present QuickShell Sharing is Caring about an RCE attack chain on QuickShare. So, this is me. My name is Yair. I'm the security research team lead at SafeBreach. I have more than 7 years of experience in security research, including research on Linux, embedded and Android systems, and for more than 4 years now, my primary focus lies in vulnerabilities in the Windows environment, which I really enjoy. So, this is Shmuel Cohen. He is a primary contributor to this research, same as I. So, all credit goes to Shmuel Cohen as well. Now, let's see what we're going to talk about today. We're going to start with the reasons for why we chose QuickShare as the primary target for this research. We'll then move on to get a quick overview about the protocol that it uses. We'll move on to see how we managed to fuzz this protocol and how also we changed our research approach and the vulnerability discoveries that came out of both approaches. Later on, we'll see how we managed to assemble a very creative and unconventional remote code execution chain, and we'll finalize with takeaways and a link to the GitHub repository. So, for those of you who are not familiar with QuickShare, QuickShare is Google's nearby file transfer solution for Android. That is how it was started, same as Apple's AirDrop. Yeah, just like that. Now, the reasons for why we chose QuickShare as the target are a few. First of all, Google has recently announced a Windows version of QuickShare, allowing to share files between Windows computers and Android devices, or just Windows computers. Second, Google at CES 2024 announced that they are working with leading PC manufacturers like LG to expand QuickShare to Windows PCs as a pre-installed app, making it a much more attractive and valuable target. Another interesting thing is that QuickShare uses a variety of communication technologies, and as far as we knew, it was Google's first time using such native APIs of these communication technologies in Windows, so we thought that there will be more room for mistake. Looking for past research, the only one that we could find that was related was done in 2019, and it was done only on the API that QuickShare uses because QuickShare didn't even exist back then. It was done only on Android and no CVEs were issued. Another interesting fact is that most of the application's code can be found in open source repositories, so that would be helpful as well. And concluding all of these facts together led us to evaluate QuickShare as a valuable and likely to be breached target. Our goal was to achieve the first ever remote code execution on QuickShare. But in order to do that, we had to start with understanding the protocol as it had no documentation. Therefore, the first thing that we did was to find the two most basic functions that allow receiving and sending packets. Then we found the read and write functions that were a part of the base endpoint channel class that was the base class for all communication technologies, allowing us to see all sent and received bytes. Then deeper inside the read function, we were able to see that received bytes are parsed into an object called offline frame. Now, this object was not a normal object as it was a protobuf object. Basically, this is the definition of the offline frame protobuf object. That's a protobuf language. You compile that into CPP files, and then you get an object that you can serialize and deserialize from bytes. And this is how our first tool for this research was born. That was called QuickSniff. Basically, it was a DLL that we could inject into QuickShare on Windows. It hooked the read and write functions, and then it parsed all the sent and received bytes into offline frame object and printed them textually so we could understand what's happening in a file transfer session. And therefore, I'm now able to provide you with a quick overview of this protocol. So, first of all, QuickShare is based on an API that is called Nearby Connections API. It implements it and adds its own proprietary implementation over it. Nearby Connections API allows apps on Android to exchange data nearby without going through the internet, so that's regardless of network connectivity. And a few interesting facts about Nearby Connections API is that it is based on protobuf. For encryption, it uses Google's library that is called UKey2. Then in order to distinguish between each app that uses Nearby Connections API, each app advertises its own service ID, and there are multiple connection strategies. We are going to focus on the peer-to-peer strategy, which is the one that Quickshare uses. Okay. So, in this strategy, there's an initiator and a responder, much like a client and a server. The initiator is the one to send the file, and the responder is the one to receive it. The communication starts with the initiator sending a connection request packet followed by a UKey2 client init packet. This is answered by the responder with the UKey2 server init packet, and then the initiator replies with the final UKey2 client finish packet, completing the encryption handshake successfully, ensuring that all subsequent packets will be encrypted. So the devices have exchanged keys. After that, both devices send a connection response packet indicating that they would like to accept the connection. And from now on, according to the Nearby Connections API, these devices are considered connected, and this is where the proprietary communication of each app that implements Nearby Connections API begins. Now, when I'm saying proprietary communication, that's not just sending raw bytes, but the Nearby Connections API offers a set of packets that the ones that implement it can utilize. These are the packets. So far, we saw the connection request and connection response packets, and from now on, we'll mainly focus on the payload transfer packet and bandwidth upgrade negotiation packets, because these are the ones that Quickshare mainly uses after the initial connection. So, if you remember, the point where we stopped is just where the connection has been established according to the protocols, according to the API's protocol, and Quickshare starts its own implementation. So, after the connection has been established, what we saw is that both devices exchange a payload transfer packet. Now, we didn't quite understand the contents of this payload transfer packet, but looking deeper inside, we were able to understand using another protobuf file that we understood that there was another protobuf structure hidden inside that was called paired key encryption. Now, in that same form, the devices later on also exchanged a payload transfer packet that contained a paired key result structure, and we didn't quite understand their purpose. But using a few experiments, we were able to understand that these packets enforce Quickshare's device visibility modes. So the device visibility modes define the entities that are allowed to send files to the current device. There are 3 visibility modes. You can set them to everyone, contacts, or your devices, which means that you are able to receive files only from devices linked to your Google account. After device visibility modes were enforced, the initiator sends a file introduction packet with some information about the file that it would like to send. The responder is prompt, finally, with something in the UI, so it's prompt with file introduction dialog, hopefully presses accept, and that triggers an accept packet to be sent back to the initiator. The initiator knows that they can now send the file, and they send the actual file, the raw file, over a payload transfer packet. So now we understand pretty much the basics of how the protocol looks like from a network perspective. Now, let's take a final look at how this looks like from a user's perspective. So we'll just see how a file is sent from a computer to a phone. So here we're on the computer. We choose an Android phone. the Android phone presses accept, and the file is now located in the downloads folder. Makes sense, right? Okay, so once we had the basic understanding of the protocol, we could start fuzzing it. For the fuzzing infrastructure, we chose the most basic one for Windows, which is WinAFL. And for instrumentation, we used Dynamo Rio. Then in order to mutate only the values in the protobuf structure without ruining the validity of the protobuf structure itself, we used libprotobuf mutator that was developed by Google exactly for that. And then after a lot of effort and sweat, a lot of bug fixing and errors, we got to a point where our fuzzer runs, and each iteration fuzzes an entire Quickshare session while we mutate one of the packets each time. Now, we did get it to run, but it was pretty slow, as you can see. However, we did, the fuzzer did came up with some reproducible crashes. However, unfortunately, these crashes were not exploitable. They were indeed reproducible. We could reproduce them, but not exploit them in any way. Another finding by the fuzzer was a reproducible timeout. This reproducible timeout allowed us to bring Quickshare into a state where it continuously opens a file in a loop that we choose from the victim's downloads folder. Okay, but at this point, we didn't have a lot in our hands to implement an RCE. We got a fuzzer running, but it was pretty slow. We did find some reproducible crashes, but they were not exploitable. So we decided that instead of perfecting the fuzzer, we're going to shift an approach to do some logical vulnerability search manually. And then we realized that, boy oh boy, we wished we had done it sooner. And the first vulnerability that we found, and I'll introduce to you here today, is a file acceptance bypass. So, if you remember, in order to send the file, just before the initiator sends the actual file, the initiator waits for an accept packet to be sent from the responder that indicates that the responder really wants to accept the packet. But thinking about the fact that Quickshare's code was so generic, complex, and filled with threads and async methods all over the place, we just thought, what will happen if we just skip the introduction and accept dance, and instead just immediately send the raw file over a payload transfer packet? The result was that this just completely successfully worked. The file was written to the victim's disk into the downloads folder without any need for acceptance or a file introduction dialog. And not only that, this also bypasses all the device visibility modes. So even if the victim device is set to receive files only from devices that are linked to the same Google account, then we could still immediately, without any need for acceptance, place a file on a victim's downloads folder. So without further ado, let's watch the first demo for this talk that demonstrates exactly that. What we'll see here is an Android phone without any files in its downloads folder. Then we'll run our exploit and we'll see how a file just appeared to be there. So we see that the Android phone is configured to receive files only from devices linked to the same Google account. And we see that the downloads folder is empty. Now, we move on to the Windows PC to run our exploit. And let's see what happens. So the exploit ran successfully, and a file appeared in the downloads folder. Okay. Now to the second vulnerability that we found, which is forcing the victim to connect to our Wi-Fi access point. But in order to understand this vulnerability, we must understand what Quickshare names as bandwidth upgrade negotiation, which is both a type of a packet and a name of a process that happens in Quickshare. So basically, bandwidth upgrade negotiation refers to the process where Quickshare can change the communication technology that it uses in order to achieve better transmission speed. It can shift the communication technology to WebRTC, Wi-Fi, Wi-Fi Direct, Bluetooth, and even a Wi-Fi hotspot. And in this process, one of the devices sends the details, the SSID and password of the Wi-Fi hotspot to the other device, and then the other device connects to it. So in the past, researchers have already shown, in that research from 2019, they showed that this can be leveraged for a man-in-the-middle attack on Android devices that can force them to go to the internet through your rogue malicious Wi-Fi access point. However, this attack lasted for about a maximum of 30 seconds, and it was since then already mitigated by Google. Today, if you force an Android device through bandwidth upgrade negotiation to connect to your Wi-Fi access point, then it will not use the internet through this access point. However, testing the exact same attack on Windows resulted in the Windows computer just going to the internet through that Wi-Fi access point, meaning that we can force any Windows Quickshare device to connect to our Wi-Fi access point in order to sniff its internet traffic. So we now can be a man in the middle for about 30 seconds. Okay, cool. So far we found 8 vulnerabilities, including the ones from the fuzzer. And they were nice. There were some vulnerabilities that were more critical, but it was still not the holy grail that we were looking for, which is remote code execution. So at that point, we just invented a sentence. And the sentence was, standard stones may sometimes be forged into deadly drones. We wanted to believe that we can take these seemingly basic vulnerabilities and combine something unconventional out of them to still get our RCE. Now, as a reminder, the abilities that we had were first to create files in the downloads folder of the victim without approval. We could force the victim to connect to our Wi-Fi access point for about 30 seconds. We could crash Quickshare in multiple ways, and we could also force Quickshare to continuously open a file that we choose in the victim's downloads folder. And enumerating these abilities raised an insight. The insight was that we can place files in the same folder where the victim downloads files to in the browser. So browsers download files to the downloads folder, and so as Quickshare. And this insight raised an idea. The idea was that what if we can overwrite an executable file that was downloaded to the downloads folder by the browser just before it's being run by the user? In order to do something like that, we'll need to first be able to leverage the man-in-the-middle technique in order to detect names of executables that are downloaded, and we'll also need to somehow escalate our ability to create files in the victim's downloads folder to overriding files in that folder. If we could do that, then we'll be able to run code. And the simplest example would be a user that downloads the latest VS Code installer. We then use the man-in-the-middle technique somehow to detect that this is the file that is downloaded. We then overwrite it if we manage to escalate our ability, and only then the user runs the file, actually running our code. So it was true indeed that we still did not have these abilities, but since we believe that the man-in-the-middle technique can somehow serve us to identify names of downloaded executables, we started with making the Wi-Fi connection last longer. And a very simple solution came up for that. We understood that we just need to prevent Quickshare from reaching to the logic where it comes back to its original Wi-Fi network after the bandwidth upgrade negotiation, right? So what we did is that we just used one of our crashes to crash Quickshare right after it connects to our Wi-Fi access point. Then it just does not come back to its original Wi-Fi network, resulting a forever lasting Wi-Fi connection. But what about the rest of the RCE? How are we going to continue to exploit QuickShare if it crashed? Well, when QuickShare is installed, it creates a scheduled task that runs every 15 minutes, checks whether QuickShare is running or not, and if it's not, then it just runs it. So we can continue to exploit QuickShare sometime between 0 seconds to 15 minutes after we crashed it. So we have our two first links in the RCE chain, which we believe that will come in handy for identifying names of downloaded executables. Now let's see the reason for why we thought that they will be so handy. And this is the reason. Metadata matters. So it is indeed true that internet traffic is mostly encrypted, and when you browse the browser and download executables, this is done over HTTPS. But even though HTTPS is encrypted, it still has two very important elements in its metadata. The first one is server name indication. So HTTPS is encrypted using TLS, and the first message in TLS is a client hello message from the client, and this message contains a server name indication extension indicating the domain to which the client is trying to connect. So if we are a man in the middle and we can sniff internet traffic of a victim, then even if they use HTTPS, we can still enumerate all the domains that it connects to. The second element present as part of the metadata of an HTTPS is the approximate size of the download. So it is true that encryption might add some random padding, but even though that's the case, the size of the download still stays relatively the same. So the conclusion is that if we can know domains that the client connects to, the victim connects to, and we know the approximate size of the download, then we can also very accurately guess the name of the executable that is downloaded. For instance, if we know that a client downloads 95 megabytes from code.visualstudio.com, then what can that be? Of course, that will be the latest VS Code installer. Installers are also much bigger than most other resources in such websites. And so we framed and defined our new man-in-the-middle technique more specifically. In order to be precise as possible, we understood that we need to define what we called domain paths. So even though the VS Code installer is really downloaded from code.visualstudio.com, in other cases that might not be the case. For example, in Notepad++, when you press the download button, you're really behind the scenes redirected to github.com, which redirects you to GitHub, to objects.githubusercontent.com, and the file is really downloaded from there. But if we'll just look at the last domain, we won't be able to tell that that's Notepad++. So we have to follow the domains that came before, which is a domain path. So to conclude, this is how we defined our new man-in-the-middle technique that we invented. We start with mapping domain paths to famous and popular executables with their sizes. Then we wait for the victim to hit a certain domain path, and once that happens, we start counting the TCP data that is transferred from the server to the client. Then if the size is equivalent or a bit bigger than the size of the executable that matches this domain path, then we know that it's probably this executable. And by doing so, we added another link to our remote code execution chain, allowing us to detect names of executables that downloaded by the victim. But we still need a way to overwrite files in order to achieve the RCE, if you remember. Though the thing that we realized is that we, of course, tried to escalate the vulnerability that allowed us to create files into overriding files, but we couldn't. After we couldn't, we realized that we don't need this ability to be so generic. We could have this ability working only for our specific situation, and that's while files are being downloaded, while the download is ongoing. But in order to get into that, we must first understand the basic download process in Chrome. So, when Chrome downloads a file, it starts by checking if the file name already exists in the downloads folder. Then if it exists, it decides that the final name for the download will be the same name with an index number surrounded by parentheses. Then, after the final name for the download has been set, the download starts, but into a temporary file with a CR download extension. Then, when the download is finished, that file is being renamed to the final name of the download that Chrome decided on at the beginning of this process. So, we thought that there is good potential to create confusion if we send a file to the victim's downloads folder right in the middle of this process, that is, after the final name has been decided on, but still was not created. We thought that it will maybe fail Chrome in overriding the temporary file to the final name of the download, leaving our file in the downloads folder. But in order to know the name of the file that we need to create, we must wait for the download to be finished because we need to know the approximate size of the download, right? That was the man-in-the-middle technique that we talked about. So how can we know that the download is finished and know the approximate size without the client knowing that the download was finished, renaming the file? What we did was that as the man-in-the-middle, we waited for the last TCP packet to arrive from the server to us. Then we held it without moving it forward to the client. And at this point, we know that the download is finished, but the client does not know that. Right at this moment, we send a file to the client, creating the final name for the download in its downloads folder. And we hoped that Chrome will fail to rename the temporary file to that final name. We released the last TCP packet, and unfortunately, this did not work. So basically what happened is that Chrome just successfully overwrote our file. So our file was just deleted from the downloads folder, and Chrome reported that the download was finished successfully. Clicking on the installer really runs VS Code. So this was a failed attempt. However, we realized that all that we are left to do is just to somehow prevent Chrome from being able to overwrite our file. And then thinking about it for a while, we realized that we might already possess this ability. So if you remember, one of the abilities that the fuzzer found was to bring Quickshare into a state where it continuously opens a file that we choose from the victim's downloads folder. What we thought about was maybe that after we send our malicious file to the victim, right after that, we'll also force Quickshare to continuously open our file in a loop. And then maybe if Quickshare uses our file, then Chrome will fail to overwrite it. And we tried that, and that actually was the best scenario that we hoped for. Once Chrome finishes the download, the result is that it deletes the temporary CR download file. It fails to overwrite our malicious file. In its user interface, it reports that the download was finished successfully. And clicking on the download file, on the downloaded file, in Chrome's downloads window, actually runs our malicious executable. So this concludes the remote code execution chain that we were hoping for, and by adding two links that we just saw. And finally, this is maybe the most important slide in this talk that you've all been waiting for. That's the demonstration of this remote code execution chain. What we'll see here is that we'll start from the attacker's perspective. We'll see the attacker's computer. We'll see how they set the hotspot, how they search for victims, choose a victim, and then we'll move on to the victim to see how they change their Wi-Fi network because of the attacker, and see the rest of the exploitation. So, the attacker sets the mobile hotspot, and we can see the IP of that hotspot. Then we are searching for victims. We found test machine. The victim chooses test machine. Let's see what happens to test machine. It's connected to safe breach. Now it disconnects, connects to test AP, quickshare crashes, resulting in a forever lasting Wi-Fi connection, and the attacker can see all the domains that the victim accesses. Now the victim just goes into the Spotify website to download the latest Spotify installer. We can see that the downloads folder has only one directory, nothing inside. So the victim downloads the file. Now let's see what happens. File is downloaded successfully, we run it, but our executable runs instead. Now let's see another example. The victim goes to Noted++'s website, surfs inside, presses on the download button. We can see that the attacker sees all the domains of the victim on the side. So the download is now finished, and we run it. Let's see what happens. The same executable runs. But it was not exactly the case. We found two more, actually. One allowed us to create a very limited path traversal to the parent folder of the downloads folder, but it had to be a very specific name. And we also found another denial of service vulnerability that we found manually, but they were not helpful for creating the remote code execution chain. So overall, we reported 10 different vulnerabilities to Google, and they were very cooperative. They issued fixes for all of them. But as we do with most research, after fixes has been issued, we go and see how they were implemented and hope that there will not be any surprises. But unfortunately, in this case, there were two surprises. So the first surprise was in a fix for one of the denial of service vulnerabilities that the fuzzer found that was caused due to invalid UTF-8 continuation bytes in file names. So it's okay if you don't know what that means, but basically the example that we provided to Google was a file name that starts with null terminator, which caused this exact exception that says invalid UTF-8 continuation bytes. Google's response to that was to issue a fix that checks that there are no null terminators in the middle or in the beginning of a file name that is sent. So, of course, we can bypass this vulnerability if we just exchange the null terminator with other invalid UTF-8 continuation bytes, and we result another crash. But that was not the big surprise. The big surprise that we saw in the fix was about the vulnerability that allowed us to write a file without acceptance remotely. What we saw once the fix was released was that when we ran our exploit, then it's not that the file that we sent was not created. It was created, but later on deleted. So apparently Google, instead of not creating the files in the first place, they added logic that after that they had identified that this file was created, they deleted. And they identified it as an unknown file. So of course we thought that there is room to bypass this fix. And here you can see in the code that they're looking for unknown files, and then they delete them from disk in the end of the file transfer session. But thinking about how we're going to bypass that, we realized that Google probably identifies somehow these unknown files. And it's probably a certain ID or something, and we knew that in a payload transfer packet, that is the one used to send the file, there is a payload ID. So our idea was that in a single file transfer session, we will send two payload transfer packets with two different files, two different names, two different contents. However, we'll set the same payload ID for both payload transfer packets, hoping that Google maybe will just delete one of them because they have the same ID. And that worked. So sending 2 files just created the 2 files, and one got deleted. So this will be our final demo for this talk. So you'll see how we're running the new exploit. 2 files created and 1 is left. So we're running the exploit. Refresh, you see 2 files are created, then only 1 is left. Thank you. Okay, so as I already mentioned, Google were very cooperative. So regarding their cooperation, really, I have no complaints. Thank you, Google. Your response, you were very responsive. This was their original response to the original report after we reported the first 10 findings. Google decided to issue 2 CVEs for the 10 vulnerabilities that were reported originally, and then a third one for the second bypass that we saw just now, with 2 files created and then 1 left. Okay, so we covered pretty much everything from the technical side, but let's talk about the takeaways, which are at least as important. So, my first takeaway from this talk is that standard stones may sometimes be forged into deadly drones. What I mean by that is that sometimes you find seemingly basic or unimpressive abilities that might not be the exact thing that you were looking for. However, sometimes you have something in your hands that you can create a very unconventional or creative flow with that will still achieve the thing that you're looking for in an indirect way. The second takeaway shifts to the defensive side, and that's that many products leave known issues and bugs unfixed because of prioritization. Some bugs seem like they raise only a minor security concern or no security concern at all, but sometimes fixing these issues may be the crucial thing for mitigating a much more crucial security risk. So for example, in this RCE chain, if we wouldn't have the ability to crash Quickshare, then we wouldn't be able to create a forever lasting Wi-Fi connection, disabling our entire remote code execution chain. And lastly, it's crucial for organizations and vendors to develop software to focus not only on specific programming mistakes like memory corruption, and when they evaluate a program security, it's also important to take a broader perspective, look at intended logic and business logic of the program, and think whether there might be some logic that can cause a security risk even if you intended to implement it, such as the one that allows us to force a device to connect to our Wi-Fi access point. And with these takeaways, I'll finalize the talk. I want to thank you all. This is my contact and social details. Also, Shmuel's details are written down below. This is a QR code for the Quickshell repository, so you'll be able to find all the files, all the tools that I presented here today, including the sniffer, the implementation of the RCE, tools that allow you to send files and use the protocol by yourself. So this is pretty much it. We can move on to questions. Thank you.